The purpose of this video is to familiarize everybody with Gauss's law, its common applications, and its common solutions. So we'll start off with our learning goals and objectives. Our first learning goal is to understand the conceptual basis for Gauss's law and electric flux. The second learning goal is to know the big picture reason to use Gauss's law. The third is to be able to recognize when to use Gauss's law and apply it successfully. And the fourth is just a general reminder that E fields obey superposition. Okay. So, if we start with Gauss's law, which is more conceptual in nature than you are used to thinking about. So I will just draw a rectangle here and then fill it in. So this is going to be our little black box. We have no idea what's going on behind it. But what we can do is we can say that so this is just a hypothetical situation. So we can have some electric field that comes in, some electric field that comes out. And if we do that all throughout this box, so imagine that this is happening in 3 dimensions and not just on the plane of this paper. It also sort of goes into and out of the paper so that it's a 3D object. So what Gauss's law does is it's a way for figuring out the electric field due to some charge distribution. So what we remember is that electric fields start on positive charges and then they either end on negative charges or at infinity. So if you were to look at this and I was to say that the red was an E field and then I was to ask you if there was any charge behind here, and I can do that now. Is there any charge behind here? Make a guess. Also, I will draw another scenario. So imagine that this is a sphere and not just a circle. And then what we can do is we can have E field lines coming in. So E field lines are coming in on all directions, not just in the plane, but in the full 3-dimensional life. So take a second and make a guess if you think there's any charge enclosed here. Is there any charge behind this little black, in this black box? Is there any charge in this black circle, or black sphere? So now that you've had a moment to think about it, I would argue that there is no charge enclosed here, because the amount of electric field lines that are coming in equals the amount of electric field lines that are coming out. So there's no origin of electric field lines. There is no positive charge that's creating some or negative charge that has them ending. Whereas in this case, all the electric field lines are coming in, but then we don't see any coming out. So this is a spot where we would expect, so I would say no Q enclosed here. And here I would say that there is a negative Q enclosed because we have electric field lines coming in and ending. So conceptually what we just sort of walked through was the idea of electric flux, which phi it's usually written as phi underscore E, and this is the E field dotted into the area. Or for more complex shapes, you can think of this as the integral over a closed area of E dot dA. So what this is saying is you taking the electric field at all the little different points of area, and then you're adding up all those fluxes to get some total flux. And if phi E is 0, so the amount of electric field times the area coming in equals that's leaving. So that's what we have up here. Phi equals 0, then there's no charge enclosed. And if phi e does not equal 0, like up here, then charge is enclosed. So Gauss's law, formally written out, is the E dot dA, and on the right side we have the charge enclosed, and then we just have this constant that makes all the units nice, epsilon naught. So we can ask, why use Gauss's law? The answer? Well, think for a second about what the answer is. Our answer? We want an E field. That's why we use Gauss's law. There is some charge distribution, and then we want to figure out what the E field is from it. So, in Gauss's law, the way you want to go about solving these problems is you always want to draw a sketch so that you have an idea of what's going on, then draw where the charges are, and then draw the electric field following the electric field line rules that we went over in class. And then you already know the electric field direction from your picture because you've drawn it. So now all you want to do is you just want to find the magnitude from Gauss's law because you already know the direction. And then what you want to do is Gauss's law needs highly symmetric situations. So what are the common situations? So common situations. So we can have point charges or spheres. These could be either uniformly dense charged spheres or they could be conducting spheres. It doesn't necessarily matter. All they need to do is have sort of spherical symmetry, so it could be a dot, or this could be something that it's a little ball. So we'd have this. When you have this, if you are outside of it, then the sort of Gaussian surface that you enclose, so it's going to be just a sphere that encloses this, has an area of 4 pi r squared, so that's the area in this case. We could also have a cylinder. So this will be something like this. And then we could want to find the E field. So you could find the E field outside of this or inside of this. And likewise, you could also find the E field outside or inside of this. So what you want to do is you want to draw a concentric cylinder, so a cylinder that's big enough to encapsulate this. So it's going to have some length. It's going to be L. And then it's going to have some, so this is going to have some radius R. And then this is also going to have some radius R. So the area here is just going to be 2 pi R L. And usually this L will cancel out because usually in something like this you're given, a charge density, so a charge per length. The length will cancel. And then sort of the last is the sheet, an infinite sheet. And this will be something that looks like a rectangle that has, some thickness, so it's a slab of charge. And then usually the Gaussian surface is, you can either draw a cylinder facing the other way, so it's coming out here, or you could draw a rectangle box. It doesn't particularly matter. All that you need to remember is that the sides here are will be the only ones contributing to the flux, because these lines, which should be perpendicular to this slab, are going to be oh, that's what I meant to say. This area right here is pointing into or into the page or out of the page, so it's either coming out you, and this is perpendicular to the direction of the electric field, which will be downwards. So this area is just going to be twice the face. So things to remember: the electric field here is going to be proportional to 1 over r squared, so it's going to get weaker as you get further away. This will be proportional to 1 over r. This could also be a line of charge. It doesn't necessarily have to have thickness. And this will be E field constant everywhere. So the idea is we pick a Gaussian surface that will have the electric field be constant everywhere, so we can pull it out of the integral. And then we just have to write down these surface areas, and then we can set them equal to the charge enclosed and the epsilon naught, and we can figure out what the electric field magnitude will be. And it will, in the end, go something like this for these three. And then if you had multiple sheets or multiple cylinders or multiple charged spheres, what you could do is one at a time add up their solutions, and by superposition figure out the net electric field. All right, thank you very much. Hi all, I just wanted to make a point of emphasis that this is the E field outside, and this is the E field outside of the charge distribution. So when you're outside all of the charge, then this is how the E field will go. And when you're inside, it will be different. So if it is a uniformly distributed charge distribution, then this E field will actually grow linear. So it'll be proportional to R. So that's just something you need to keep in mind, that if you are inside of this, likewise with the sheet, if you're inside of any of these, then these won't necessarily be what you find. These are for outside of them. So this is also outside. Thank you very much.